How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to be diving into IPv6 addressing. So what I'm going to do out of the gate is I'm going to talk about the addressing structure first before I get into the different types of addresses and where they're used and all that good stuff that goes along with that. And the reason why I'm doing that is because as we get into the addressing types and we start breaking down how the different address types are formatted, it'll help if you understand the address build, if you will, and how it's put together. So unlike IPv4, which is a 32-bit address, which is binary of 0 through 9, and typically in the context of, you got your 1, 2, 4, 8, 16, etc. The issue with IPv6 is that it's hexadecimal, so it's got numbers and letters, and can look very similar to that of a MAC address. So when you dig into IPv6, which is a 128-bit address, you get an I won't say infinite, but I want to use the term infinitely large number of addresses. So it's kind of like a euphemism where it's not really infinite, but the reality of it is it's so many addresses that it's not likely that you're going to run out of address space. So the address format is important to understand. So just like we went through with IPv4, we're going to go through and break down IPv6 and how that comes into play. So without any further ado, let's go ahead and dive into this. So I'm going to bust out my pen tool here, and we're going to do some whiteboarding. So the first thing that I want to do is I want to put this into context of what this is going to look like, because the address breakdown is going to be different than that of IPv4. Where IPv4, you had the 128, 60, the 64, 32, 16, 8, 4, 2, 1. And depending on, because if you take all of this right here, you add them up, you get 255, right? So, and if you turned all these bits on, that's 255. Well, and that one. So that works out. That math works just fine. But this is considered a byte. This is 1 byte. Why is it referred to a byte? Because a byte is 8 bits. Where in IPv6, we only have 4 bits per block. So if you got 1 byte is equal to 8 bits, what is 4 bits referred to? Well, for those of you, it's actually ironic. It's called a nibble. I'm not making this up. I mean, literally, it's called a nibble. A nibble is half a byte. So when we talk about the addressing structure, you're actually only going to be using this part. Now, the interesting thing about this is when you use 8, 4, 2, and 1, if you add them up, 8 and 4 is 12, 12 and 2 is 14, 14 plus 1 is 15. Well, what's interesting about that is you have 0 through 9. That's a 0. But what about the other 6? Well, you've got A through F. So what I'm going to do is I'm going to break this down for you to how it's all broken out, and then to me, IPv6 is somewhat easier to understand because you're dealing with half of the binary pieces, right? Half the binary half of the switches or half the bits aren't there. So with that being said, we're going to have a bunch of different nibbles. So the way you would break this out is you're going to have 8, technically it's going to be 4-bit breakdowns. So the way, well, technically, that's not exactly true. So here's how it's actually going to be formatted. So we're going to take our 8, 4, 2, and 1 at the top. I'm going to go ahead and get out of the way just so that you guys can see it better. So what's going to end up happening is you're going to have obviously a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we're going to have A, B, C, D, E, and then an F. So the way this, and we'll do, over here we'll do a 10, 11, 12, 13, 14, and then a 15. So the way this is going to work, 0 is obviously going to be all zeros across the way. A 1 is going to be 0, 0, 0, 1. A 2 is going to be 0, 0, 1, 0. A 3 is going to be 0, 0, 1, 1. A 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. A 6 is a 0, 1, 1, 0. A 7 is a 0, 1, 1, 1. An 8 is a 1, 0, 0, 0. A 9 is going to be a 1, 0, 0, 1. A 10 is going to be a 1, 0, 1, 0. An 11 is going to be a 1, 0, 1, 1. A 12 is going to be 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. And then, last but certainly not least, we're going to have a 1, 1, 1, 1. So now that you can see how they're all broken up, and I've done my best to try to line them up, but you see the correlation, right? Well, now that we have the bits broken down, what we are able to do then is these guys right here, when they are put together, you're going to have each one of these 4-bit nibbles is going to make one of 4 numbers inside of the address block. So you're actually going to have 16 bits that you have to allocate for. Meaning you're going to have one of 4. So let's say, for example, the address 2001 : 1, 2, 3, 4 : 5, 6, 7, 8 : beef. Oh, that's supposed to be an F. So BEF. BEEF. This right here would be a IPv6 address. And so when you're doing these 4 bits right here, is going to be one of these numbers right there. So you're going to have one of 4, meaning that you're going to have to do this thing right here, this breakdown, 4 individual times. So you're going to have, this is 16 bits right here. This is 16 bits here, 16 here, and 16 here. 16 and 16 is 32, 16 and 32 is 48, 48 plus 16 is 64. So that is why the breakdown is important. So if I was to start breaking this number down, 2001, what is the binary equivalent to the 2001? Well, that equates, it's going to be, this will be a 0010. This will be all zeros, obviously. And this is 0001. Now 1, 2, 3, 4 is going to be a 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0. That's going to be what 1, 2, 3, 4 looks like in binary. 5, 6, 7, 8 is the same thing, right? So what ends up happening is you get 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then 1, 0, 0, 0. And the reason why I know where to put them is because I'm always using this as reference. The 8421 is, just imagine there's an 8421, 8421, 8421 sitting on the top, and I know which bits to turn on and which bits to turn off. A B, in this case here, a B I know is going to be an 11. So an 11 is going to be a that'll be a 1, 0, 1, 1. An E is going to be a 1, 1, 1, 0, 1, 1, 1, 0, and then 1, 1, 1, 1. And that's really how you do this across the board. That's how the individual pieces are put together. So what we just did in a very short amount of time is we were able to take 64 individual bits and break it down to binary. This right here, all this information right here, is how the computer sees it, right? We see it based off of the binary equivalent to what we're trying to understand. So now that you see how that's broken down, the address structure, which we're going to go into here in a little bit more detail, has a couple of options because it's so long. So if I was to take a really, really big address, say, 2001 colon 6789 colon 2163 colon dead beef F1 echo 9 1776, and then let's say 2011. That would be a fully written out IPv6 address. Each one of these is 16 bits because you've got 4, 8, 12, 16. So this would be 32, this would be 48, this would be 64, and the repeats. So we'd have another 16 plus 64, that'd be what, 80? 80, 96, my 112, 112, 128. So this is how you would break it down, right? Now, the interesting thing about this, you can take an IPv6 address and you can break it up into two different sections. You got the left side of this here is the network, and then the right side of this here is the host. It splits it right down the middle. Where the subnetting comes into play is you're typically going to have a /64 is your average IPv6 address space, meaning you're going to allocate based off of /64 addresses. Now, the way that this works out is this right here is a very long address. Now, what's cool about IPv6 is there's ways to shorten up the address size to make it more palatable, easier to deal with, stuff like that. And the way that you do this is these colons here, this is going to be your, obviously your dot and dotted decimal is replaced with a colon. When you get down to the shortening of the address, there's a couple ways that you can do that. Any leading zero, so if, for example, if you've got 2001 colon 0100 colon 0000 colon 1119. If you have a leading 0, and I drew this out the way that I did on purpose, any 0 that is the leading 0, meaning it's the first nibble in your 16-bit section of your address, this 0 can actually be shortened, and it can be you basically can drop it, meaning that the 0 won't be there. So you could actually rewrite the value is 2001 colon 100 colon 0000 colon 1119. Okay, now you can only do this one time per address. So you could drop the leading 0, the first 0 in your 16-bit block. That's one way to do it. The other thing you can do is, let's say for example, let me go ahead and erase this and take this back a little bit. Another variation of this is this. You can say, let's say this is a 9. Well, what you can do is 2001 9100. You can take any 16-bit block right here that is all zeros. You can actually take the zeros and translate them into double colons. Or actually, I take that back. My apologies. You can short it down to a single 0. So your address would then be 2001 colon 9100 colon 0 colon 1119. Now, if you have a whole bunch of, if your IPv6 address is basically 2001 colon 0000 colon 0000 colon 0001, what you could do is you could actually shorten this portion of it right here down to colon colon. So colon colon can be used to represent these 8 zeros. So it would look something more like this: 2001 colon colon. And remember what we talked about up here, where you can take the leading 0. The leading 0 can be dropped, and then it would literally just be a 1. So these 3 zeros here in the front can be replaced with 1. So your 2001 colon colon 1. Now, what's interesting is this is still a /64 address, because you got to remember, we're talking, and I drew this intentionally on the left side of the network. So this is still all net. Now, the interesting thing about how IPv6 addresses work is the address types really come into play and how you dictate what address is going to be what. There's multiple address types. Now, the reality of it, and I'll step back away from the address formats and the types for just a minute and talk real world for a minute. In my 15 years of being a network engineer, I have only dealt with IPv6 in public networking, meaning where I actually had to deal with internet-related connectivity 2 times. One of which was working for a colo customer that had IPv6 deployed, and I was the only one on the engineering team that knew anything about IPv6. So naturally, I was the one that had to deal with the IPv6 stuff. So I did try to teach the other guys that I worked with, but our workload didn't really allow me to teach them anything. So that was one. The other one was a financial customer that I worked with for a while, where we ended up purchasing through through Aaron, and justification, we ended up getting the customer a /48 address space. We never did anything with it other than having them buy it because they claimed that they had a need for IPv6. They never once deployed it, at least nothing to my knowledge. So these are the scenarios that I've ran into in my career. So the reality of whether or not you're going to get a large address space through Aaron, it really depends on you as the engineer. So we're going to talk about IPv6 as we get deeper into it. The interesting thing about IPv6 is 99% of the things that work in IPv4 work in IPv6. So there are some very minor nuances that aren't the same, but for the most part they are. So it's not like you have to go relearn any of the routing protocols to understand how they work differently than they would if they were IPv4 unicast than if they were IPv6. So when we talk about IPv6, we are going to run them in parallel. So that's another thing that I get a lot of questions on is the customer I'm working with is rolling out v6 or they have a v6 presence. Do I need to worry about that with IPv4? No. They're two different address families. So you never need to worry about v6 overriding v4 unless there's a directive or direction the organization is going and they want to replace v4 with v6. And there could be some problems with that if you decide to go down that path. It's not necessarily a bad direction, it's just you need to understand the complexities of that. So in my experience, I've never had a customer go full v6. There might be a v6 presence, but especially here in the US, we don't really see a lot of v6 unless you work for a service provider or you have a co-location footprint where v6 is rolled out. Beyond that, I have never seen anybody deploy v6 in production. So now, not saying that nobody does it, it's just I haven't seen any. Every customer that I've ever worked with has a v4 presence, and that is how they do their routing, is v4. So that is what I'm comfortable working with. Now, I do know how to do dynamic routing for RIP, EIGRP, OSPF, BGP, IS to IS, all of the MPLs, VPNs, DMVPN. I'm familiar with how all of them work. So when we get into the weeds and we start looking at the routing tables and standing all this stuff up, it's not impossible to understand. It's just I will be walking you through how to use the different routing protocols to do their thing. I am not looking at doing basically what I won't be doing is any exhaustive v6 coverage. So we will do mostly v4, and when we do get into v6, it'll be here's how you stand up the protocol, here's how you get it working, things like that. So there won't be a drive to get it configured a certain way. So there are some things to keep in the back of your mind when you're looking at v6 that will come into play. And the number one thing that I always get asked on is, if I deploy v6, do I have to get rid of NAT, network address translation? And the answer to that question is it depends. So got to remember that IPv4 is more widely deployed than v6 is, even 15 years after I got in the industry. And I was not long after I got into the industry, I'd say early 2010s, where there was IPv6 Day, where all the service providers in the world decided they were going to flip the switch and become IPv6 relevant, I guess. I also remember there being a big talk about how that v6 will eventually replace v4. We're in the mid 2020s or almost there, early 2020s, and I still don't see that happening anytime soon. So when we talk about it, it's going to be because there's a blueprint, an exam blueprint that talks about it, and we need to cover it. Beyond that, I have very few times have I ever had to go in there and actually work with it. I've spent more time, seriously, I have spent more time going through and testing out how V6 works in preparation for the route switch lab, the service provider lab, and for a handful of customer things that I needed to do at a short consulting gig that I did many years ago. And that is the extent of my V6 experience. Now, if you're over in Europe and there's a much larger stance, well, it is what it is. So that's just something for you to keep in the back of your mind when you are looking at how V6 operates. Now, the way that V6 works in terms of the address allocation, there's a few different ways that it works. There is a auto addressing capability that's known as stateless auto address configuration, or SLAC for short. And what SLAC does is SLAC will take the 48-bit MAC address of the interface and will use that as part of the IPv6 address. And what it does is it will take, and regardless of the MAC address, it'll take the MAC address. Let's say you've got A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. Is that 1, 2, 3, 4? I think that's too long. It's 48 bits. 4, 8, 2, 4. Why am I having a hard time with this? This is not confusing myself. How long is a, we just pull up my command prompt and we're going to look at ipconfig /all. Yeah, so it's AB, so in this case here we've got, it's 48 bits. So we have 8, 16, 24, 32, 40, 48. So if I was to do, 2, 4, 6, 8, 10, 12. So 2, 4, 6, 8, 10. I need 5 and 6. So what would end up happening is we'll just do 5, 6. And so it'll be 2, 4, 6, 8, 10, 12. There we go. So let me go ahead and get rid of this. I needed to look what a MAC address's format was. So what'll end up happening is you'll take your MAC address, your AB, and let me actually rewrite this so it's easier to understand. So you'll take your A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. Right, you got your colons in here, breaking everything up, and in the middle, right here, you'll take this set, and what you're going to do is you're going to inject by adding 2 more of these sections here, F, F, colon, colon, F, E. Now, what's going to end up happening here is when you do this, this is what they refer to as the EUI 64. I think this stands for Enhanced User Interface, EUI, but I don't quote me on that one. I don't believe that's the actual case. But what ends up happening is this address changes slightly. So what I mean by that is you have this capability where the beginning of the address, and remember we talked about this in IPv4, we talked about the high order versus the low order of a address space, where the high order is going to be always the bit furthest to the left, the low order is going to be the bit furthest to the right. What ends up happening is you take the seventh most significant bit and you turn it on. So you go from 0 to 1. And what ends up happening is this B would end up getting changed to something else. So you take the seventh most significant bit and you turn it on. Or if it's off, you turn it on. If it's off, you turn it. If it's off, you turn it on. If it's on, you turn it off. And that changes this. So the B, in this case here, the B, and if you're not sure what the seventh most significant bit is going to be 8, 4, 2, 1. This is 4 bits. And then you got 8, 4, 2. This is going to be 3 bits. So whatever's the 2, so in this case here, it's going to be this one. For a B, it's going to be this 1. If it's turned on, you're going to turn it off. So, and actually, let me just double check to make sure that my process is still correct. I am mostly sure that that is the case. So if we talk about the IPv6 7th bit, why flip 7th bit? Why is the 7th bit flipped in IPv6? To make it easy for it, okay. It determines whether the MAC address was universally or locally assigned. And let me just look this up real quick, because it's been a long time since I talked about this. The seventh most significant bit, 0, is the value of the universal local bit to include global scope. G is individual group. So, and then the M bit is the manufacturer. So, inverting the universal bit when forming the interface identifier is to make it easy for the system administrator to hand configure local scope identifiers when hardware tokens are not available. In other words, the value of the 0 indicates universally administered. For instance, the 7-bit will be 0. So that means if it's turned on, right, meaning there's a 1, right, because right now we've got the 7th bit right here for our AB. Our 7th bit is turned on currently. And then because right now it's a B. If I was to turn this bit off, so take the 2 right here, come down here and turn this off, that would make this a what? A 1 1, a 1 0 0. A 1 0 0 makes it a 9. So instead of it being a B, this bit right here would be a 9 because it would be turned off right here. So it'd be A9 is what it would eventually come out to be. Now, the concept of that is to indicate whether it was universally or locally assigned. If you are using EUI64, automatically assume that the 7th bit is going to be turned to 0. Therefore, it would be set to 0. Now, if you were to go and assign, to manually change the MAC address, you were going to go in and set it, you are manually modifying the global, the universally already assigned. If you were to go in there and manually modify that, the bit would not be turned off, it would be turned on, because you are going in there and manually modifying it. Therefore, you're turning it on. So instead of it being a 0, you'd be making it a 1, whatever that would be. And so it would turn out to be a 1 by default because you'd be turning it on. Or in this case, it would be a 2. So the actual nomenclature would be 0200. Because this right here, you got 4 here and you got 4 here. Yeah, you got your 8421 here and you got your 8421 here. You are modifying this bit manually, so you turn it on in the 2, so it automatically would get a 2. So you're basically wiping out the other 4 bits. You're basically resetting that. So what I don't want you to do is I don't want you to get hung up on the concept too heavily on this. Just be aware that if you are going to go with EUI64, that the bit is more than likely going to get reset. Meaning that that B, even though I say it's supposed to be a 9, I'm pretty sure that, and we'll verify this later on, that what will end up happening is that 9 would get reset to a 0, so it would be A0. It's been a while since I've played with it, and I haven't done the research to figure out which way it's going to go, because to me it's more of a trivia piece to understand how that comes into play, because the reality of it is this. When I do any IPv6 addressing in the lab that we're going to be walking through, none of it will be universally assigned. I am going to manually assign all of my IPv6 addresses because that'll make it that much easier when we're looking at the routing table and we're looking at trace routes and pings to determine where something is. That is why whatever the device IP or device number is, so if it's going to be, XR43 or, Nexus 66 or whatever it is, the device number, or depending on where it's at, will be in the IPv6, the IP addressing, so that it's easy for us to identify it. So that's one of the capabilities. Now, since I've gone over this, I wanted everybody to just be aware of the whole 7th bit being flipped, because that's how EUI64 works. So as long as you understand that, then you're in a good spot. And that's what I really wanted you to understand and how that comes into play. So you can either leverage what I would refer to as the OUI MAC, the Organizationally Unique Identifier. If you take the OUI MAC and then add FFFE to it, the MAC address, the 7th most significant bit, will get flipped to a 0. And now if you go through and you manually modify the MAC, which the reality of it is nobody ever does. I don't know anybody that's ever manually modified a MAC address. Especially if you're doing it on any type of grand scale. Now, one thing that I do want to make mention here is the address types. Where is that hiding? Right here. And I did a little bit of the address types, and I'm just going to go ahead and share this. I literally just did a Google search for it. I'm going to go ahead and clear the screen off. So if you want to, I would take a screenshot of this before we go any further, just so you can understand how this comes into play. So I'm going to go ahead and clear the screen. And this guy right here is what I wanted you guys to, I want to talk about it. Instead of trying to just write it all out, I figured I would just do a quick Google search for this, and we'll just talk about the specifics. So there are some capabilities in here that we need to understand. So we have unspecified. So this automatically assumes that the interface that we're working with doesn't already have a IP address. And if it doesn't, that's fine. But this address may only be used as a source address by an initializing host before it has learned its own address. So it'll automatically have a ::/128. And : would mean all zeros. There is no address already applied. Now loopback, when we talk about that, is going to be a ::1, or in our particular case, if we go back over here to our topology, what we would end up doing is, for example, one of the things that I've done across the board, and I think I've done it for every device up to this point, or it's labeled, but what I'm going to end up doing is the per service provider, because that's my intention when we get into the dynamic routing section, is to go through and use public IP address spaces, and then what we're also going to be doing is all of our dynamic routing, the CCNA and some CCNP level content, well, I'd say the majority of it, will be done in this environment, these little block of routers. So as we're going through the demonstrations of how this technology works and the design concepts and all that type of stuff, it'll be a small enough topology to make it make sense. So that's essentially where I'm going with that. So when we talk about how like loopbacks will work, if I was to pull up this guy right here and look at, say, R26, and I don't have any IPv6 addressing applied yet, but if I was to do a show run interface loopback 0, there is a /32 host IP address, so it's a /32 mask applied to 1.0.0.26, and I did that on purpose because when we get into dynamic routing, that'll be my router ID for my device, whether I'm dealing OSPF, EIGRP, BGP, ISIS, whatever it might be. That'll how that come into play. IPv6 will be doing the exact same thing. I will come in here and I'll just type in : whatever the device's ID number is, /128 to give it a host IP address. So that'll be essentially what that'll look like. So that's what the loopback address. This address is used when a host talks to itself over IPv6. This often happens when one program sends data to another. Not that important. We're not really going to talk too much about IPv4 mapped. That'll come later on down the road. So this will come into play when you are dealing with embedded IPv4 addresses inside of IPv6. One use for this is in dual stack transition scenario where v4 addresses can be mapped into v6 addresses. So we'll talk more about that. You're converting v4 into v6. That gets more complicated. Unique local addressing. This is one we're going to be spending quite a bit of time on. We're going to be using the FC00 block. And what we're going to do is, remember that : thing I talked about earlier, where if you have a block of zeros, all 4 zeros, the : 0000, 1 2 3 4, that block of zeros can be notated as : So it makes it allows you to shorten up the address space to be something much, much tighter and easier to write out, honestly. IPv6 addresses can be a pain to write out. So what we'll do is in our topology, for example, is anything public, right? We're going to use like a 2001, because if we look down here a little bit further, our global unicast is going to be 2000 : 3. Right? That's going to be the address space that we're going to be able to use. So you can do, a lot of people use 2001 or 2001 DB8, which is good for documentation. This is an RFC defined address space. So there's that. So what we'll end up doing is we'll grab like a 2000 address space : so I'll go back over here. So like this right here would be this 1.26.27.0/24 will be notated as a 2000 : 1 : 26 : 27/64. So that's how I will notate them as I go through. So then when we look in the routing table and we're starting to do IPv6 with BGP, for example, or any routing protocol for that matter, it'll show up as a 2000 and then whatever the device IP address is. Now internally, for any type of our internal routing where it's RFC 1918 address space, the 10.172.16 or the 192.168, I will be using FC addressing space, and then FC, and it'll be 10.2.22, 10:2:22:/64. The idea is to use all four of our network blocks in the beginning, and then we will use the slash, the fifth octet, right? So it'll actually look something like this. Let me duplicate this real quick, just so you guys have a reference of what I'm talking about. So these guys over here, this will look more like this. This will be a 2000:2:29:43. It's supposed to be a colon, right? So we have our four blocks, right? We have 2000:2:29:43, and then we'll do another colon, and we'll say /64, right? That'll be our address range. So by doing that, this will essentially be the IPv6 address space for that particular range. And then on either end, this will be ::43, this will be a ::29/64. Is how that'll come into play. And that's essentially the addressing scheme that I'm going to be using. I'm not going to really put this in until we get further into the weeds on how V6 works, but that's essentially the breakdown. The same thing will apply for our FC. I'm going to click here and duplicate this. What this will essentially look like is this. This will be FC. FC0, I think, right? FC0. FC00, yeah. FC00. FC00 :10 :1 :22 :/64. That's what the internal address will look like when we get into doing IPv6 in the core. So it'll be FC00 :10 :1 :22 :/64. And then what will end up happening is I'll put like ::22 ::1, things like that as we go along. That's what the structure is going to look like. And that's how it'll be discernible. Now there are some other addresses out here like FE80 called link local. And what we'll be able to do, for example, is there's a capability when we do this, because what will end up happening when we get into the routing is we will see stuff propagated based off of MAC address, because the EUI64 will kick into play. Even though we're manually setting our IP address, we're not manually setting our MAC. So it'll automatically grab the MAC. So what we'll end up doing is I will go in and say, at the interface level, this is going to be something FE80 : something link local, and it'll give us an indicator of what interface or the device that we're attached to. So I'll talk about that more in detail later, but essentially what I'll do is I'll go to say interface gig 0/0, I'll type in IPv6 address will be FE80 : 26, and then I'll say link local, right? And if I do a show IPv6 address or interface brief, we can see that FE80 : 26 is there. So when 27 goes to see this, it's not turned on, but if I was to do a show IPv6 neighbors or show IPv6 route, we would see an FE80 : 26. So it would give us an indication of who we're talking to. And that's the go forward plan that I have with you guys, so that it'll be easier for us to understand who's talking to who and how. So there's that piece. So I definitely would recommend you Google these different variations and you'll understand what they look like. So you understand what Teredo tunnels are. This is a mapped address allowing V6 tunneling through V4 NATs. Excuse me. There's a benchmarking one. There's a 6 to 4 where you're tunneling. One of these in here is the other one that we're going to get into is going to be multicast. And multicast, just like multicast with the 224/4, so what they were commonly referred to as link local multicast, that has its own multicast address space in IPv6 as FF00. So what will end up happening is you're going to see a lot of the stuff that translates. For example, the RIP version 2 multicast address is 224.0.0.9, where the link local multicast address will be FF00::9. So if you're not ever sure on that, all you have to do is come over here to our best friend Google and type in the RIP NG link local multicast address. And it'll be FF02::9. And then if you want to know about, say, OSPF v3, that's going to be FF02::5. So whatever it is in IPv4, it'll more than likely also be in, well, they are, I know, in IPv6. So these are the references that you need to make when we're diving into how multicast or IPv6 works. Overall, it's not terribly complicated to understand. And we already broke down, how the addressing structure works and how that comes into play. There are ways to summarize it. So if you were going to take a very large address space, you could break it down into a smaller address space or vice versa. There are ways of going, /96/128, /127, 126, things like that. You can summarize to make things more efficient, stuff like that. And just be aware that /64 in IPv6 is basically the same thing as /24 in IPv4, where if you wanted to get like a /20 in v4, you're looking at a /48 in IPv6. And so the bigger the address gets, meaning the smaller the mask, /48, /32, things like that, typically indicates the size of the organization or how you're getting it from a standards body. So if we were to talk about that from a perspective of, let me scroll down here real quick. If we're talking about that from a push out, if we're talking Aaron, right? Aaron is more than likely going to hand out for a ISP, they might hand out a /32, right? They hand out you a /32 v6 address, which is going to encompass things like /48 and /64. So you might get 65,000 /48s. And so what's cool about that is, because they have such a large address space, if they are a tier 1 ISP, like an AT&T or a level 3, I'm not sure who else is besides AT&T who's a level 1 ISP, they'll be able to hand out to like a tier 2 ISP a /48. And then they might be able to give out multiple tier 2s. But you might have a tier 3 service provider that's only like local to a particular area. They might get a /48. So then you have, it dwindles down from there. So most of the customers that I worked with that have address space, that's what they get. Whether you're a service provider or you're an end customer, you get a /48. So you get a very large address space. So it gives you, 65,000 roughly /64s. /64s are going to equal essentially a /24. Now you can get further in. You can break that down if you'd like into like /96, /126, things like that, and get into summarization. But the reality of it is that just about every customer I've ever worked with doesn't do IPv6. So if you want to know more about the addressing structure, there's some really good documentation out online that goes into this and how it all works. And I would definitely recommend you guys dig into that if you are looking to take any one of the Encore, the NRC exam, stuff like that. This stuff will definitely come into play, and that's one thing to note. So I don't deal with the V6 ever, so my level of experience with it is not going to be that wide or that deep beyond what I'm going to be walking you guys through. So configuration wise, when we get into how it works and stuff like that, that'll be getting the routing protocol to work, V6 and stuff like that. We'll make it happen, and we'll get into the weeds of how those things work. However, the idea is to build enough of a foundation so that if you need to take it a step further, at least you know where to look in the right places. You're able to Google. Your Google foo is strong enough to get you through whatever it is that you need to. So we're gonna work our way through that, and I just wanted you guys to see some examples of what that would look like. But the end state is basically get the routing protocol stood up V4, do some basic stuff with V6, and then stuff like that. We're not going to take V6 terribly far. So that's just one of those things to keep in the back of your mind. There is we talked about the multicast with the FF02. One we haven't talked about is going to be Anycast. Now Anycast is not unique to V6. It's just a V6. There is no broadcast. So there is no broadcast. So V6 uses other mechanisms besides ARP, neighbor discovery, neighbor solicitation, things like that to handle those capabilities. IPv6 Anycast is the concept of multiple devices or multiple locations in the network all sharing the same IP address, and you're leveraging the shortest amount of hops to the closest one. That's the one you're going to go to. So if you have for example, if you live in my general area, let's say you're in Chicago and you're trying to reach Google. Well, geographically speaking, you're going to take the closest quad 8 Google device, whatever device in your general area is hosting quad 8. That's the device that will be responding to you if you ping or trace route to it. However, if you live in, say, LA or in, Las Vegas or somewhere in the UK or Asia Pacific, you are going to take a different path, and a different device is going to be responding to your quad 8, because there's not just one device on the internet that uses quad 8. So if you're trying to ping 8.8.8.8, there's going to be that's considered to be an Anycast address, because it's not typically, doesn't have to have the term Anycast necessarily. There are some caveats to that, but in most cases when you're looking at Anycast, you're looking at just a regular IP address that's been configured on multiple devices. Now, a thing that is commonly used in VXLAN EVPN environments, this also applies to SD Access and ACI and Nexus Dashboard and things like that. When you're looking at you've got a spine 1, spine 2, leaf 1, leaf 2, leaf 3, leaf 4, and you've got border 1 and border 2, and you've got these guys all connecting like this, something like that. What will end up happening is the leaf switches will all have devices attached to them. Well, there's this thing called the Anycast gateway address, and the idea here is that if you've heard of HSRP or VRRP, both of these are gateway redundancy protocols where essentially you've got two devices talking back and forth to each other and over some sort of trunk link, and then what ends up happening is you've got a LAN segment southbound, right? You've got a switch sitting here and you get devices plugged into it. What will end up happening is that HSRP VRRP, there is a virtual IP and virtual MAC address assigned for that gateway redundancy mechanism to respond to your end users. So regardless of if this guy's up or if this guy's up, one of the two is going to be responding to your end user's requests. Now, Anycast gateway works similar to that, but instead of it being two devices communicating with each other, each one of these leaf switches, regardless of how many SPIs are configured, so let's say you have 50 SPIs for all of your VLANs sitting on these leaf switches, every one of the SPIs has the same MAC address. And you use the command fabric forwarding mode Anycast gateway. And what that does is it turns this feature on where every box in your fabric, regardless if it's ACI, SD Access, or VXLAN EVPN, everybody is sharing the same MAC address. So you're going to route to the closest one. If you're attached to leaf 4, you're going to route to leaf 4. If you're attached to leaf 3, you're going to go to leaf 3. And the idea here is it doesn't matter. You can migrate anywhere in the network. You might be vMotion from a server attached to leaf 3 to a server that's on leaf 1. Your gateway MAC address doesn't change, because there would really be no way of a server attached to leaf 1 to be able to then also be connected to leaf 4. That wouldn't make any sense. So unless leaf 1 and leaf 4 are wired to each other, which they normally wouldn't be. Now, there are cases where you could do things like VPC and VXLAN together. That complicates it, but it does work. That's what they refer to as Anycast VPC, because both switches would essentially be needing a unique IP between the two of them, and it's Anycast at the same time with them too. We'll get into that more in detail later on. I'm actually going to be demoing Anycast Gateway when we do. I'll scoot up here and clear the screen. When we start doing, we're not going to do any VPC with VXLAN. Over here, we're going to be doing VPC. We'll do a VPC between Nexus 50 and 51. But we will be doing Anycast Gateway here on 56 and 55, where server 40, all the servers will be able to talk back and forth to each other, but both the SPI for 172.16 and 100, that will be the same MAC address across all the leaf switches. But we'll cross that bridge when we get there. So that's essentially what Anycast is. You're going to route to the closest node that has that IP address. So Anycast does come in handy in certain situations. This is one of them. So that is my breakdown for y'all when it comes to V6. So there's going to be a lot more to cover. So again, we're going to be looking at dynamic routing, static routing, stuff like that when we get into the weeds and how all that stuff works. What I don't want you to do is get tripped out on it. There's lots of documentation online. If whatever I'm breaking down doesn't make sense or it isn't clicking with you, That's okay. Don't, whatever you do, don't get frustrated at whatever I'm covering. If it's not clicking, go use the Googles. Open up Google, open up Safari, whatever web browser you want to use, search engine you want to choose to use. Ask Siri, whatever question you have, and do some more research on it. That's the benefit of today's internet. So, if you have any comments, questions, concerns, feel free to drop a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.